Good morning and welcome to AP Statistics. Today we're going to begin Chapter 3, Scatterplots and Correlation. I'm going to assume for the moment that we all understand what a scatterplot is, and I'm just going to draw one for you. So let us assume that this scatterplot is correlating, which means associating two variables, and this is the general pattern of our scatterplot. A scatterplot is always going to graph two quantitative variables, numerical values, because the values you see are coordinates on the scatterplot. So let's just say it's hours spent studying, and let's also just presume it's a GPA, grade point average scale. So it's going to go in increments of 1. It doesn't much matter for right now. The point is, a scatterplot, number one, is points of data on a coordinate grid. First thing. They're always numerical. And what you're looking for in a scatterplot is a trend, a pattern, what's happening. So in this particular scatterplot, what we see is as we move forward on the x-axis in a positive direction, we're moving upwards on the y-axis in a positive direction. So we call this positively correlated. Correlate, again, means a coordinate relationship. So how does x impact y? Also understand that x, the independent variable, is what impacts y, the dependent variable. Y doesn't impact x. There's a vocab word for that. And in addition to just calling it independent and dependent, the vocabulary is the x-axis is our explanatory variable, and the y-axis is our response variable. And again, we're looking for a correlation. It doesn't always happen that we have a pattern that is truly explanatory in response. I could graph two totally unrelated things. There could happen to be a pattern in the data. Doesn't mean that x causes y. Be careful with the word causation. Okay, so this is a positively correlated data set. And if you were to put a line of best fit through it, which I know you've done before in Algebra 1, it'd be the line that pretty much approximates the direction of the data and cuts through the center of the data points. Now, we've called it a line of best fit thus far. It's actually called a least squares regression line. We call that an LSRL for short. There's a reason why it's called a least squares regression line. Also, the way it's drawn by the calculator when you have it do regression is that it takes all of these vertical distances of each data point from the trend line. See all those vertical distances? The vertical distance of each data point from the line is essentially the amount of error we've found when trying to make a prediction. For instance, if I studied for 3 hours, I'd predict a GPA of 2.5, whatever, it doesn't matter. But the distance from the data point to the line that predicted it is called a residual. Residual basically means leftover. So it's essentially the leftover distance between the observation and the expectation, what we thought it would be. When an observation is above the LSRL, it's a positive residual. It's more than expected. When the data point is below the LSRL, it's got a negative residual because it's lower than expected. So what's it doing? Well, imagine that we made a square of that distance for each one of these data points where we have that distance. Whatever that distance is, whatever that residual is, we're going to make a square using it as the length. And what the LSRL, the least squares regression line, does is it tries to put the line in such a place that it minimizes the area of all of those squares when added together. I know it's kind of a difficult concept to truly imagine what's happening, but suffice it to say that the combined area of all of those squares is as small as it can be. because if the line moved anywhere else, it would increase the residuals in such a way that the area total would be larger than it is right now. That's why it's called the least squares regression line. It's a better line than, or better name rather, than saying line of best fit or even trend line. They're both accurate words, but LSRL is the one we're going to go with. Okay, so the LSRL minimizes the distance, minimizes all the residuals to the point where it's as small as it can be. Yeah, sure, there are still some values that have larger residual values and result in larger squares, but still this line is showing you the smallest sum of squares that it can be. Now, correlations can be positive if the slope of the LSRL is positive, meaning as you move forward on X, you're moving up on Y. The correlation can be negative as well, if as you moved forward on X, you're moving down on Y, and that's of course a negative slope. If the LSRL doesn't really have directionality, meaning, let's say this is your scatter plot, okay? That scatter plot doesn't really go up or down. So the LSRL would be a horizontal line. Now the slope of a horizontal line, as you know, is 0, which is also the correlation you're seeing here. There's no correlation, even though there's a line that can be drawn. The correlation we're looking for is the impact of X on Y. And a horizontal line shows you that no matter what X is, Y doesn't change. That means that there is no impact of X on Y, so there is no correlation. Now, there's a number out there that tells us how strong that correlation is. Let me go back to this for a second. You see how all those dots were pretty close to the line? There's two that are larger residual values, but they're pretty close. There's a number that your calculator is going to give you. Yes, there's a formula for it, but it's very complicated. We don't use it. There's a little letter called R. And when you do what we're about to do, which is called linear regression, the R value shows up and it tells you basically how strong your correlation is. It also tells you the direction. If it's a positive R value, it's a positive correlation. A negative R value, a negative correlation. Now, R is always something between 0 and 1. I'm sorry, -1 to 1. 0 to 1 is R squared, which we'll do in a moment. The closer your R value is to the extremes, the more perfect it is. So if you have an R value of 1, that basically means that you've got a line graphed in the space where everything falls exactly on that line. It's perfect. If you have an R value of -1, it's also perfect, but in a negative direction. As they move in towards 0, they become less perfect. So there's distance off the line. A 0, as you already saw, is totally uncorrelated. The points are everywhere. There's no directionality. So this line would have an R value of 0. There's no correlation. This line would have an R value closer to 1. It's positive, so it would be closer to 1. And it's pretty good, pretty close. When it's pretty close, you're looking at something in the 0.9s, maybe 0.85 to 0.95, in that vicinity. We really are looking for R values that are at least 0.8 to show any kind of strength. Below 0.8, from 0 to 0.8, or from 0 to -0.8, we're looking at weak correlations. They're not very good. Okay. Now, let us look and hopefully just remember how to do linear regression. So what I'm going to do is give you just a couple of points of data, and we'll try to do some regression from those points of data. So if you have your calculator with you, that's great. Obviously, we're going to need it. So I'm going to give you just correlated data. We'll say X values can be just 0, 1, 2, 3, and 4. And Y values can be 10, 7, 5, 5, and 2. So these are 5 coordinates, and what I want you to do is get your graphing calculator and enter in that data. So while you're doing that, I'm gonna go grab mine. Hold on. Where are we gonna enter the data? That's the question. And the answer is our lists. Okay, so all of my good calculators are on loan to the PSAT, so I'm gonna use this older one. What I want you to do is enter your data. So you go to Stat, and you go to Enter for Edit, and there's where our lists are. And I'm gonna clear out what I've got here. So I'm gonna clear and then Enter. And I'm gonna enter my X data in L1. My X data, 0, 1, 2, 3, and 4. What happened to my 0? Let me try to do that again. Okay, so I got 0, 1, 2, 3, and 4. Now, so far so good, here we go. The Y data goes in L2. So we got 10 and 7 and 5, 5 and 2. Okay, as we can probably see, as X increases, Y is generally decreasing. So we're looking for a negative correlation. How do we do linear regression? I'm gonna show you real quick, all right? First thing I want you to do is make sure that your diagnostics are on. Depends on the calculator you have. Some of you, when you hit mode and scroll down, you'll see where it says Stat Diagnostics and turn it on. I have an older calculator in my hand. It doesn't even show me that, so I can't use that. So if you have an older calculator also, you can't get there with mode. So here's what I want you to do. Go to second 0 for the catalog and just scroll on down to where it says Diagnostic On. All right? So put your cursor next to Diagnostic On and you just hit Enter twice and it's on. What that does is it'll allow you to see the R and the R square value. We'll talk about R square in a moment. Now, we want to go to Stat and then over to Calc. The 8th one down on most calculators says Lin Reg A plus BX. That's the one you want, A plus BX, not the first one, A plus BX. Stat Calc 8. And again, newer calculators will prompt you for the inputs. This is an older one, so it's not prompting me. So you want the XList data to be L1. So in an older one, it opens up a parenthesis. I'm gonna say second one for L1. You would also in your newer calculators. Then go to the Y-list data. If it's an older one, hit a comma. Now, the Y-list data is in L2, so second 2. And then it says store regression equation. You want the calculator to store your regression equation. So you want it to put it in the Y1 menu, which is where all of our lines usually go. And to get there, you hit the vars button. You go over to Y vars. You hit enter for the function. You hit enter for the Y1. Now, we're ready to go and we're gonna calculate it. So hit enter and it gives you the information. So what's it telling you? Well, first of all, it tells you that it's going to give you the equation in the format y equals a plus bx. Cool. Then it tells you what the numbers are. So what I have here, I have an a value of 9.4. I have a b value of negative 1.8. I have an r square, which we'll talk about in a second, of 0.9310. I have an r value of negative 0.9649. This lets me put together the equation of the actual trend line, the LSRL. The equation is y equals 9.4 minus 1.8x. That's the equation of my trend line. Now the R value tells me its strength, and this was a negative, so it's a negative direction, 0.9649. That's exceptionally strong. So you want to say that when you describe the R value. It's a very strong negative linear correlation. The R value is called a correlation coefficient. That's its real name. It tells you strength and direction. The R square is obviously the R value squared. That's pretty simple. It's called the coefficient of determination. And here's what it tells you. It tells you the percent of the variability in the data that's explained by the linear relationship that we're seeing in this equation. So in this case, about 93% of the variability, which is the distance of the points off of the line, about 93% of that variability is explained by this linear relationship. And that's a really, really good thing. So what we're looking at is a model that's probably pretty well linear. You could also graph it to check it out. So here's what I want to do to graph it. Go to second y equals and turn a stat plot on. And the scatter plot's the first one you see, so leave it on there. You want L1, L2. And you're going to just zoom 9. Zoom 9. Oops, I have other stuff in my, look at that, it's coloring an inequality. So I'm going to just erase that. Should have checked that first. Go to your y equals and make sure that you don't have any extraneous things in there like I do. Okay, so once again, it was 9.4 minus 1.8x. Your equation should be there in the y1. So once again, I'm going to try that graph with zoom 9. It shows me the scatter plot as well as the LSRL overlaid on top. You can see how close the points are to the LSRL, which is why it has a very strong R value. The residual values are very small, and it's a negative direction. Cool. Now, all that being said, we have to be very careful when we actually use our LSRL. I can use my equation to predict values for y based on x, and that's really good. And because it's a strong relationship, I know I can have pretty good accuracy. However, when I predict within my domain, between 0 and 4, I'm safer than when I predict outside my domain. Predicting inside your domain is called interpolation, and it's usually fairly safe if you have a linear pattern. Extrapolation is when you choose a number that's outside of your domain, predict for x equals 10 or -5, and I don't really know what's going to happen there because there could be a reason why my domain was as limited as it was. Be very careful when you're extrapolating. The values don't always really hold up, but interpolating, it's pretty safe. Now, homework was attached to the Google Classroom announcement on page 163. There are multiple choice, numbers 27 to 32, and that's all you've got to do for today and for the weekend. The homework is due Monday morning by 7 a.m. Let me know if there's any problems or questions. Send me an email and I will help you out. Have a great weekend and a happy Halloween.